Hi everyone, my name is Yuri and these are my co-authors, João, Bruno, Rafael and Fábio. I will present our work called as Decision Support Framework for the Stock Market using Deep Reinforcement Learning. That is the outline for this presentation that starts with the motivation for this work. Then I will explain the decision support framework based on deep reinforcement learning. Then I will show you the results and the conclusions that we made, and finally the references. The stock markets are very crucial to expand the economies in the entire world, since it brings the opportunity to the individuals and the companies to spread their risks and receive large rewards and profits. The investors seek for the best investment decisions in order to maximize their profits. However, 90% of the traders lose their capital since the stock market is a very complex system, and the artificial intelligence have been applied to support those investors, and according to the references, the application of AI can maximize the profits by more than 28%. In the state of the art, a decision support system was created for investing in the stock market by using one-against-all neural networks technique, and their strategy was to use the relative strength index overbought oversold. Also, a new investment strategy was built to optimize gains on investment in the stock market, also based on neural networks, and their strategy was the 9.1. In this paper, we propose an AI framework based on deep reinforcement learning to learn trading rules and recognize patterns. The reinforcement learning techniques map situations to maximize the numerical reward signal. In this sense, the reinforcement learning model is continuously updated, and its combination with deep learning allows it to solve long and short memory prediction problems simultaneously. Here we have the main block diagram of the decision support framework that starts with the Yahoo Finance, that we retrieve the data with Python web crawler. Then we do some data transformation and store it in a relational form. Then we do the calculation of technical indicators and trading setups. In the next step, we do the feature selection and dimensionally reduction. Then we do the classification and prediction with deep reinforcement learning. And the final step is the visualization tool of the decision support framework. Now, I will explain these two blocks highlighted here. First, the following strategies were added to the deep reinforcement learning model Learn and Identify, that are the moving average convergence divergence MACD standardization and the continuous point CP. The four most used technical indicators group were chosen, resulting in 12 technical indicators to serve as features. Then we applied feature selections because its purpose includes the removal of irrelevant features and to improve the algorithm's performance. We applied the variance threshold technique, resulting in the inclusion of 6 features: the simple moving average, exponential moving average, MACD, relative strength index, on-balance volume, and maximum. At this moment, I will explain this classification and prediction with deep reinforcement learning block. This diagram shows the main necessary steps for our framework in order to build the deep reinforcement learning model. First, we pre-processed the 6 features, and the model had 3 possible actions to take. Then we compared each predicted action with each setup action to give the reward to the model. Then we update the policy with the loss function, and we backpropagated it to the deep neural network. The deep neural network technique includes the creation of a multi-layer perceptron. This multi-layer perceptron was built with the input layer, 3 hidden layers, and the output layers. And after each interaction, the agent learns more and acts until the last possible state. The visualization tool of the decision support framework is the final diagram and will be shown and explained in the results section. In order to compare with the state of the art, we show these 2 tables where it's possible to note that our proposed algorithm is better in terms of F1 score for long and short positions. Also, the percentage of return is more than 10% higher compared with the state of the art. Here we have the visualization tool of the decision support framework mentioned earlier. The first thing to note is that the user can select any USA stock symbol right here. Then we have this candlestick chart to know how this stock is performing with the model's advice in blue or orange of what should be done in that moment. On the right side, we have the summary of how our model is performing with that stock symbol. And it's possible to note that our proposed model return on investment was 18% higher than the Starbucks share appreciation. A deep reinforcement learning decision support framework is proposed for the stock market to support stock market investors and companies. The effectiveness of the proposed framework has been validated in the USA and Thailand stock markets with an important increase in terms of F1 score and return rate compared with the state of the art. Therefore, our work outperforms the state-of-the-art frameworks to evaluate the position strategy and the return on investment. These are the references used in our work. Thank you for your attention.
Hello everyone, this is Goklesh Tanapal and I'm here to present my paper titled Sensor Fusion of Camera and LiDAR Data for Vehicle Detection. I would like to first thank my professor João Paulo de Costa for his motivation throughout this project, and he's also a co-author of this paper. And my other co-authors Giovanni, Bruno and Gabriel, I would like to thank them also for the support they've given. So the motivation behind this paper um, is to improve the perception of autonomous vehicles, because it is a very essential to have a robust perception system to improve the reliability of an autonomous vehicle. And reliable autonomous vehicles have a huge potential to improve road safety and reduce accidents um, in the near future. And so when we have talked about fusion of camera and lidar data, the widely adopted method is decision fusion, which means the data is individually processed, like camera data and lidar data are separately processed, and then the output is combined. But this does not make use of the high level interdependencies between the two data. And the other method is called raw data fusion, which makes use of the raw data, and it fuses the raw data and then inputs them into the algorithm for further processing. This paper proposes a YOLO-based framework for raw data fusion of the camera and lidar data. So to fuse the raw data, we generate reflectance and depth maps of from the point cloud data from the lidar sensor by exploiting the distance and intensity values that are available. So this framework is based on You Look Only Once, YOLO version 3, and YOLO is a CNN-based network for object detection. It uses darknet 53 as a backbone, and the detector is a multi-scale detector as it detects in 3 scales. The output would be in such a format where it is detecting, um, giving you the coordinates of the boxes and the objectness score, how likely there is an object, and the probabilities for the number of classes. The value is 3 here because number of classes in this case was 3, but if there were more number of classes, then the value here would be 20 or 80 depending upon the number of classes. So this is a YOLO block diagram, and once you have uh, there are two main building blocks, the darknet convolution and the darknet residual. So the darknet convolution is a stack up of 3 layers: convolution, batch norm, and leaky review. And the darknet residual is a stack up of 2 blocks of darknet convolution. So whenever you see the term darknet convolution here, think it as a stack up of 3 layers, and the darknet residual is a stack up of 6 layers, 2 of these. So it's a stack of 6 layers, and when the number here tell how many of these are sequentially stacked. So darknet residual 8x means 8 darknet residual blocks are sequentially stacked. So this is the feature extractor part, and this is the um, the detector part. You can see there are 3 different scales: small, medium, and large, and there's also an upsampling between the from the larger scales to the smaller scales, so that the smaller detector can benefit from the detections of the larger scale. So how YOLO detects is for each if for each image, if you consider it as an S cross S grid, for each image it divides into S cross S grid, and each cell on that grid is responsible for detecting an object, and so each cell has 3 anchor boxes linked to it. So think of anchor boxes as predefined boxes with the height to width ratio, and the duty of the network is now to predict the deviations or the offsets of the actual prediction box, which covers the whole object. The offsets of the centers of the predicted box from the anchor box, as you can see in this image, and the ratio of the predicted box height to the predicted box to the anchor box height, and the ratio of the predicted box width to the anchor box width. So these 4 values the detector is predicting, and in addition it also predicts the confidence scores, which in 2 parts. So one is how confident it is that there is an object inside the box, and another is what are the probabilities for each class, and these 2 confidences are finally merged in the test phase. So this is a YOLO based framework for decision fusion, which we have created for comparison purposes. As you can see, there's a camera data and there's a lidar data, and they're put into 2 different YOLO networks, and then the output which is the bounding boxes are then concatenated and put into the post processing, which is the non-max suppression, where the boxes with the highest confidences are selected. The Kitty dataset. So the Kitty dataset was created by Karlsruhe Institute of Technology in partnership with Toyota Technical University in Chicago. And so it has camera data, lidar data, and GPS IMU sensors data. There was a benchmark created out of this dataset, that is the 2D object detection benchmark. It has 748 training images and 7418 test images with about 80,000 labeled objects. And for each of the image, there is a respective point cloud data from the lidar, and they also provide the calibration files for converting coordinates from one set of coordinates to other. So this is the framework for data fusion. um, what we have here is that we have the camera data, which is directly, and then we have the lidar data, which after transformation and pre-processing is combined with camera data to get the lidar image, and this combined image is inputted into the YOLO network, and we get the bounding boxes as a result, and after post processing we get the final bounding boxes. So lidar data transformation. So lidar data is usually given as a 3D point cloud data, which is then projected onto the image coordinates using the rotation and translation matrices available in the calibration files. And this projected points are then formatted into 2D array, and they are smoothened out using bilateral filtering to form a image kind of grid. So like this we generate the depth and the reflectance maps, and these two maps are added along with the already existing three channels of the image. So red, gray, blue are the three channels of the image, and to that we add two other channels, the reflectance and the depth from the lidar data. So totally 5 channels for the proposed YOLO RF method, which has 5 channels. And so these are the different models that we are going to compare. One is the base YOLO, which has only camera images as input, and the YOLO lidar, which has the lidar data as input, and the YOLO DF, which does decision fusion as discussed earlier. So training the models was done using Google Colab for about 40 epochs per model, and the first annotations were converted into a format that YOLO understands, and then they were then inputted to the training program. We calculate the a mean average precision for each of these models, and we compare them. So to calculate the mean average precision, we use the data defined, we use the criterion defined in the Pascal VOC 2012 competition, which says if the intersection over union of the predicted box on the ground truth is greater than 0.5, it is considered as a match, which is a true positive. If the area of overlap is less than 0.5, then it is a false positive. If boxes have not been detected or they have different class, then they are classified as false negatives. So from this we get the precision recall values, and from that we calculate the precision recall curve. With the area under that curve gives us the average precision, and the mean of average precision across all classes gives us the mean average precision. So this is the mean average precision for the vehicle class of all the models. So you can see the proposed raw data fusion network has the highest 78% MAP, and it is showing a 10% improvement from the base YOLO, which uses only images, and even with the traditional decision fusion technique, it is showing a 5% gain. And then these are the recall and precision values. You can see that the base YOLO has a good recall value, and the lidar has good precision. The decision fusion was not able to successfully combine these two in one model, but the RF, or the raw data fusion, was able to successfully combine both the positives of lidar and image based networks in one model. So this paper has proposed framework to achieve raw data fusion of camera and lidar data, and the modified version of YOLO to suit this network has been successfully trained on the Kitty dataset, and it has been compared with the decision fusion framework, which is again made out of YOLO. And this comparison clearly brings out the performance gain achieved by raw data fusion. Uh, Base YOLO, as I was telling earlier, the raw data fusion is able to successfully combine the recall value of image database network and the precision value of lidar database network in one network, and hence it shows a superior performance than both the networks. Even with respect to YOLO DF, it has a 5% improvement in terms of object detection performance. So thank you.
Hello everyone, my name is Giovanni Santos, and this presentation is about the improved localization framework for autonomous vehicles via tensor and antenna array-based GNSS receivers. The other authors are João da Costa, Daniel Lima, Matheus Anata, Bruno Praciano, Gabriel Pinheiro, Fábio Mendonça, and Rafael de Souza Jr. During this presentation, we'll talk about some motivation aspects related to our work. Then we'll show an overview about antenna array-based positioning systems for autonomous vehicles. Next, we'll show some first results of our research and finish this presentation with our conclusions. Road traffic accidents, according to World Health Organization, is the 8th leading cause of deaths. On average, every year, 1.35 million people die in the world due to the road traffic crashes. More than 90% of the accidents are caused by human-related reasons. And it's very interesting because vehicle-related reasons cause less than 1% of these accidents. There is a study from Intel company showing that almost 600,000 people should be saved in a period of 10 years due to the use of autonomous vehicles. Fully automated driving can bring several benefits. For example, the use of autonomous vehicle can reduce the amount of accidents because there is a transfer from human failures to technical ones. There is a efficient time usage by people because the people can work or rest instead driving, and because the efficient driving optimization algorithms, there is a lower fuel or energy or battery energy consumption. Of course, we still have to resolve many challenges to ensure that autonomous vehicles are safe. In terms of positioning, autonomous vehicle requires centimeter level error in order to avoid crashes. State-of-the-art positioning solutions based only in GNSS, Global Navigation Satellite Systems, are not suitable for autonomous vehicle context, mainly because there are several error sources that affect GNSS receiver position calculation. For example, clock errors, both of satellite or receiver, ionospheric and tropospheric errors, receiver noise, multipath errors caused by building trees, and among others. A combination of GNSS and the inertial navigation systems is normally used to minimize positioning errors. Then GNSS acts as a complement to INS. For example, GNSS provides the coordinates for INS initial start point. GNSS provides continuous information to update the INS estimates, and the INS system can continue navigating during periods of GNSS signal obstruction. Some advanced solutions already exist able to provide positioning correction in a very accurate way, such as differential DGPS and the real-time kinematic RTK. Take a look on the specification of a GNSS and the IMU device from Novatel for PPM, precise positioning management. We can see centimeter level accuracy. However, this centimeter level positioning accuracy is difficult to obtain in urban scenarios. In this picture, we can see a multipath problem caused by reflections of a satellite transmitted signal. Because the reflections, the onboard GNSS receiver installed on the vehicle is receiving many components of the same transmitted signal. One that is a line of sight component received directly from the GNSS satellite with a time delay tau loss, and several other components called the non-light of sight generated by the environment interferences, in this case reflections in buildings or trees or other objects that generated these reflections with a time delay tau and loss. This superposition of a loss signal and the n-loss components cause a positioning degradation at the GNSS receiver. One way to mitigate the n-loss effects is using antenna array GNSS receivers. Normally, the mitigation of the n-loss effect is made using state-of-the-art matrix-based algorithms, but recent researches shows that tensor-based approaches for time delay estimation in antenna array-based GNSS receivers outperforms those state-of-the-art algorithms. There are several tensor-based algorithms. For example, eigenfilter using HOSVD with FBA, subspace tracking framework, and the approach with model order selection. The authors of this paper already have several other papers showing the advantages of using tensor-based algorithms to mitigate n-loss effects. Then, in this paper, we show a framework for improved vehicle localization using tensor and antenna array-based receivers. Our framework is based on the extended common filter. And the extended common filter has two main steps, one called the prediction and the other one called the update. In the prediction step, the common filter calculates a predicted estimation ahead, and in the update step, the extended common filter uses the measurements of the sensors to generate an updated estimation. We are proposing the use of antenna array GNSS, antenna array based GNSS to receive the several signals of satellite transmission, and apply a tensor-based approach using HOSVD plus FBA to mitigate the N-loss effects and, of course, better estimate the time delay and consequently generate a better estimate, a better position estimate. Now, we show first results of our research. To this research, we have a simulation using our framework. In this case, we have in this simulation, we have a scenario with a vehicle moving from point A to point B. And during this journey, we are using a GPS receiver operating at 10 Hz and one IMU operating at 50 Hz. And we have a reference scatter, a building in this case, that is able to generate interference in the GNSS receiver. In this case, reflections of a transmitted signal and generate N-loss, one N-loss component. In this figure, we can see the GPS positioning error caused by N-loss component. Here, we can see the N-loss effect using different kinds of GNSS receiver. For example, this dashed line is referent to a standard GNSS using one antenna and with one epoch. In other words, with no data preprocessing. There is a GNSS receiver with one antenna and the key epochs, in other words, with data preprocessing. And we have a GNSS receiver using with M antennas and using a matrix approach to mitigate the effects of N-loss component, and the red line refers to GNSS receiver with M antennas and using the tensor approach. And in this case, we can see that the error, the added error to the GNSS receiver is about 60 centimeters. Now, these figures show the positioning estimation error calculated by our framework. In this case, we have a maximum error using the tensor and the GNSS and the antenna array based GNSS receiver around 30 centimeters. For example, using a standard GNSS with only one antenna, we have in the worst case 1.5 meter of error, estimated error. And of course, this value is not suitable for autonomous vehicle, for example. Now, our conclusions. Using antenna array based GNSS receivers combined with tensor-based signal processing algorithms can mitigate the multipath components and significantly improve the positioning estimation. In our simulation, we had a reduction from 1.5 meters to around 30 centimeters. Future work of our research involves evaluate other tensor-based approaches and evaluate the framework in other scenarios. Then, thank you for your attention.
Hi everyone, Igor here. Pleasure to meet you. I'm an electrical engineering student currently enrolled at University of Brasilia, and I couldn't start the presentation any other way than saying thank you, Professor Alexandre Neri. With all your support and your help, this research would not have been possible. I've seen the effort you have put into it, and I'd like to thank you. I'd like to thank as well Alexandre da Sena, who is a professor at State University of Rio de Janeiro, because he has helped us into the research as well. So let's start this presentation, a SHA-free coprocessor for IoT applications. And I need to start the presentation by talking with you about Internet of Things. The Internet of Things has modeled the way we live from a long time, and the current connectivity between people and devices made our life easier, but it does bring us some concerns with security and efficiency. It's a business evaluated in approximately $100 billion. Therefore, it's a business that will continue growing for a long time. But we need to start thinking the more connected we are, more information we provide. And in an age of green technologies, efficiency becomes a moral responsibility. Therefore, we need to look for solutions that tries to change and improve security concerns and efficiency. But I need to talk about, when we talk about security, we need to talk about hash functions. And what exactly is a hash function? A cryptography hash function can be defined as an algorithm that produces a message digest D of fixed length for a given input message M of arbitrary length, such that it's nearly impossible to transform D back into M. The image on the slide shows us a schematic that is easy to understand. We get a text, pass into this hash function as an input, and then we obtain a number. In this presentation, we present several hash algorithms, but in this presentation, we'll be focused on SHA-free. Sponge construction. In order to explain and to introduce SHA-free, it is crucial for me to talk about sponge construction. Sponge construction may be the requirement to construct hash functions. It's a mode of operation based on a fixed length permutation and on a padding rule, which builds a function mapping variable length input to variable length output. The schematic on the slide, if you search about sponge construction on the internet, you will inevitably find this schematic. This schematic helps us understand what exactly is the sponge construction, and in a cryptography context, it provides a particular way to generalize hash functions to a more general functions whose output length is arbitrary. and the applications are many in the world of hash functions, but we'll be talking about the SHA-3, a secure hash algorithm free, which were created by Michael, Guido, Joan, Ronnie, and Giles and Saf, who together won the National Institute of Standards and Technology competition contest in 2009. And this algorithm created by those researchers became the new version of the secure hash algorithm, which replaced the version 2. To obtain the digest we talked earlier is necessary to we have several steps in this algorithm, such as the sponge constructions and block permutation with 4 steps. And the schematic for each one of those steps were brought into this slide. Those schematics was obtained from the KitKat team, the team which developed the secure hash algorithm free. If the listener wants to read more about it, go to the KitKat team and the listener will eventually find those figures. But which standards definitions we need and what exactly is the SHA-3? The SHA-3 is a hash algorithm, as the figure shows us. It requires as an input a message, and it will provide us as output the digest, a unique number. And the standard definitions is that we have 4 versions of SHA-3. The 224, 256, 384, and 512. But in this research, we focused on the SHA-3 256. The applications are many. The applications vary from cryptography. From cryptography, they are used on digital signatures, public key certifications, and many others. But the SHA-3 is indeed the future of the security and the future of hash algorithms, but it does have some disadvantages. In the KitKat team website, I've found a discussion arguing about if the SHA-3 is low, and the conclusion is that it isn't as low when compared to other hash algorithms. However, it does require a great computational power, and that's one of our goals in this research. The implementation, our goal was to improve the SHA-3 efficiency using FPGA. In order to explain further our research, I need to talk about the coprocessor interface and the configuration. The overall architecture of SHA-3 system is presented in the figure in the image, in the slide, and the coprocessor was implemented using HILC specification. The listener may argue why you didn't use VHDL or Verilog in other harder description languages, and we decided to use HILC because it is a faster to prototype system. And the configuration, the coprocessor lies in the programmable logic part of the FPGA and connects to the processing system PS, part via Advanced Extensible Interface AXI, as well as to the off-chip DDR memory. The PS is responsible for controlling the accelerator operation, which includes handling input and output data. It is easier to understand what exactly the entire configuration by looking at the image. But now, what resources do we use? In this entire presentation, in this entire research, we used the ARM Cortex-A9 without optimizations of the SHA-3 code, and the FPGA, Pink FPGA, which version is detailed on the slide and on the paper. Right now, we need to talk about the code. We use the tiny SHA-3, which is a very small readable implementation of the SHA-3 hash function. This function is provided by the KitKat team on their website, and we use this code from the GitHub repository to obtain a code, a HILC code, that would work on our FPGA. If you look at the code presented on the slide, you will see that we have a lot of fragments, and this code has been modified to enable the HILC compiler to properly map the operations to a given target FPGA. Details of the code can be further analyzed into the paper, but right now I just want to grasp the attention to the lines 16 and 12, because those lines allow the coprocessor to properly communicate to the ARM Cortex A9 processors. The most important, maybe one of the most important parts of our research was the heavy workload from the tiny SHA-3. The tiny SHA-3 is an algorithm, as we said earlier, that requires a lot of computational power. And we did find a part of the code that is repeatedly, several times, there is called several times. Therefore, we provided a pipeline directive that tells, which is a function that tells the HL's compiler to produce code in the RTL architecture that allows each round to begin its computations before the previous round has finished, which significantly improves the accelerator's throughput. The result is that the SHA-3 coprocessor is 1600% faster than the available processing, and it is crucial to remember that the ARM Cortex A9 has an operating frequency approximately 6.5 times faster than FPGA. The chart on the image, the chart on the slide, shows us the result. Larger the message size, larger was our speed up compared to the Cortex A9. At the end, we like to talk about circuit error and power consumption, which it is really important to emphasize the relevance of using the SHA-3 coprocessor instead of running on the ARM processor, since it presents not only less power consumption, but also considerably better runtime, which can be seen on the image. Thank you very much for your attention. If you have any doubt, don't hesitate to contact me on the following mail.
Hi, we are here to present our work tuning machine learning models to detect bots on Twitter. This work was done by graduate students of Campinas and Brazilian universities. Although not all bots are malicious, these fake accounts are usually set up as means for other malicious activities. Fake accounts on social media have become the main channel for automated software agents, known as bots, to interact with the networks. The malicious use of bots has already been applied, for example, to manipulate opinions on extremely relevant issues, such as presidential elections in France and United States. Identifying and clearly flagging bots accounts may help users to assert better judgment on the content spread by these accounts and lessen their negative effects. There are many works that approach bot detection as natural language processing tasks. Others focus on account features in order to identify bots. In this work, we assume bot detection as a binary output problem that can be treated with a language-agnostic approach. The aforementioned works have already established how classic machine learning models have been used to achieve high accuracy with very efficient and scalable training algorithms. Our contribution is to propose a pipeline with 5 steps, from data splitting to model tests, that can handle highly accurate bot detection models. Our pipeline is composed of the following steps: data splitting, feature engineering, model tuning, model selection, model test. Our pipeline can be customized to use different feature engineering, scaling, algorithms, and different performance metrics for our model selection. We tested our pipeline with a combination of 3 publicly available Twitter bots datasets: BotWiki, Cressy RT-Bust, and Cressy Stock. We decided to join these records in these datasets in order to have a bigger sample of bots. The new dataset, comprised with the 3 original datasets, the code for the pipeline, and our experiments and the classification results, are all open source and available on a public Git repository. Several experiments were carried out to demonstrate how the pipeline is used to determine the best combination of feature scaling, performance metrics, and classifier hyperparameters. So, to better know our data, we conducted exploratory data analysis applying t-SNE. t-SNE is a probabilistic technique that helps to preserve information on the local similarity among data points. We apply this algorithm for different perplexity values, as shown in the figure. With higher perplexity values, we see some cluster structures. Nevertheless, there is no clear linear plane that could split the groups. Hence, we can expect poor results on classifiers with linear assumptions, such as logistic regression. The proximity of the projections in high perplexity also led us to expect lower results from classifiers such as KNN and decision trees, which depend on the dispersion of the data points. The set of features selected and generated in the first steps is based on prior tests and knowledge from both domain. For instance, we leverage on markers discussed in previous works, such as the presence of the digits and randomness in the screen name or alias that identifies an account. The selected features were status counts, which is the number of tweets including retweets issued by the user, followers count, the number of users following this account, friends count, number of users this account is following, favorites count, the number of tweets this user has liked in the account lifetime, listed count, the number of public lists that this user is a member of, default profile, when true, indicates that the user has not altered the theme of the account profile. Profile use background image, when true, indicates that the user has changed their account's profile background image. Verified, when true, indicates that the user has a verified account. We also constructed some features such as screen name length, the length of the screen name string, screen name digits, the number of digits in the screen name string, name length, the length of the name string, name digits, the quantity of number digits in the name string, and also description length, the length of the description string. We also tested the effects of feature scaling in the dataset. Scaling features usually lessen the effects of differences in range or scale among features, preventing features with higher ranges from capturing or introducing bias on the training algorithm. This is especially important for algorithms such as logistic regression that use a weighted sum of the features, and algorithms like KNN or SVM that are based on distance measures. Scaling also allows for faster convergence and learning. In this work, we used min-max scalar and standard normalization. In order to find the best hyperparameters for each model, we used a randomized search given by the scikit-learn library. It is a much cheaper method computationally than grid search and provides good parameters fit. The algorithm will select random combinations on the provided hyperparameter space for a given number of iterations. We used in our pipeline the following classifiers: KNN, logistic regression, SVM, decision tree, random forest, bagging, and XGBoost. After finding the best hyperparameters, the pipeline trains each model in the entire training set and verifies its performance on the validation set. Then, the model with the best score on the validation set is selected. As a last step, the pipeline trains the selected model on the training and validation sets and verifies its score against the test set. The pipeline returns the selected model and a report on its performance. We run our experiments with different values for feature scaling: none, standard score normalization, and min-max scaling. And also 3 different cross-validation scoring functions: area under the ROC curve, F1 score, and accuracy score. We fixed the area under the ROC curve as the only validation scoring function in order to be able to compare all the models. The best combination of scaling, cross-validation scoring, and hyperparameters found for each model is listed in this table. As expected, we observed better performance on the 3 Bayesian ensemble models such as random forest, bagging, and XGBoost. These models had similar performance, very similar performance. XGBoost had a slightly higher area under the ROC curve score on the test set for all experiments at about 86.4%. The results confirm that our pipeline can help build better classification models for bot detection on Twitter, as it enables researchers to test hundreds of combinations of different models, parameters, scaling transformers, and scoring function with just a few lines of code. The pipeline can also be easily extended to train classifiers for other social media platforms as well. The pipeline may also be used for researchers when comparing the training and classification algorithms. For instance, the reporting feature in the model test step can give invaluable information on the classification models and the impact of the selected parameters and feature scaling transformers on their ability to correct, classify, and account as bot. Our pipeline can also be parameterized to save defeated models after the cross-validation parameter search, so researchers could execute further tests with each model. Future work on this topic may include the usage of different datasets. Not all bots will behave the same. As they are constantly evolving, new data is crucial for keeping the model performance high in production. Unfortunately, we could not find a Brazilian dataset. It may also be beneficial to include natural language processing techniques applied to the tweet text in conjunction with account profile features. This pipeline could also be extended to support this. Another possible research path is remodeling of the classification problem from a binary output to a multi-class probabilistic model. We could consider a gradient of bot activities, from accounts entirely controlled by autonomous software agents to real accounts that have a few automated posts generated by users or platform authorized apps. Finally, it would be interesting to include dataset of different social media platforms, having to write just the dataset feed function, feature generation, and feature selection functions, which are platform specific. Thank you for your time.
Good afternoon. My name is Marcos Buendia Andrade, and today I'll be presenting a paper that was made by me and my colleagues. His name is IoT fog-based image matching monitoring system for physical access controlled through IP camera devices. So our agenda is, firstly, I will talk about background motivations, related works, proposed system, testing results, and then finally conclusion and future work. So the background motivation is that security has always been a high concern in our society. So to improve it, people use security cameras that can help a lot, but then came the biometric cameras, which improve a lot. They are better than the common surveillance cameras, and our solution is a solution is a coordination of several smart devices with a camera following rules previously determined. So this is a summarizing of a project which will be explained better in the following presentation. So we really think that this system can be used to improve security a lot. And here we have the related works. Here is a list of similar papers that we found, and here are the main difference from our proposal to their papers. And here I'll begin talking about the proposed system itself. So here we have a distributed system to identify people using security cameras distributed over an environment. So it has two main components, the camera coordinator and the smart cameras. Both components are two different softwares that together together they are the whole system. And here we have the architecture components. Here you can see the camera coordinator, the smart device, which consumes a camera, and they use a smartphone. So the camera coordinator, it is the central system that orchestrates all the smart devices. It is made in Python using the framework Flask, which is a framework for web development, and it is divided in two parts, the user interface and the API. For the user interface, it is responsible for registering two entities of the system, the users and the environment. Here you can see the user interface itself. You can see the users, the environments, and for the users, it has the following fields. It has a label, which is unique. It must be unique for its primary keys. It has an email, an identification document. It has days and an hour range. This will be used by the smart device to determine if the user is allowed or not to be at that place in that daytime. He also have a list of photos which will be used to do the face biometry, and it also has a list of allowed environments, which will be used to separate him in the environments that he can be. For the environment, it's important to notice that the environments correspond. Each environment corresponds to a smart camera. They are the same thing. It has two fields: the name and the rules. The name must be unique, for it is used to do the linkage between the smart devices and the central controller. And the rules define how the environment should build its report. The report is a text that will be sent to the user's cell phone. So here we can see that the the rules can be divided in two types: how to build the report and and when to send it. So the how to build the report tell the environment if what should it put in the report. So it should put the number of face detected, the allowed hour, the detection confidence that he had while detecting that face, and the one to send determine if the environment should send or not that report that he's building. For example, with the non-detection rule, you can set the environment to only send detections that he knows who the person is. For the API, it follows the HTTP protocol. And what does the API? The API provides the data required for the smart device of any environment to work. So what does the API do? It gets all the data that was collected by the UI and divides it for each environment. So it makes it available in its API. So you specify the environments that you want the data, you specify it in the pattern of the request, and the API returns to you all the data that environment needs to work. It is crucial for this API is crucial for the smart cameras to work, the smart devices. So now we'll talk about the smart devices. They execute a Python script, and they need to be configured. So how do you configure the smart devices? You need to configure them with the same name that you register in the UI, because that's the way they are linked by this name, which is unique. And what does it do? It fetches data from the camera coordinator. So from time to time, it fetches the data from the API to keep synchronized with the real data. And it's important to notice that all the processing that I will be talking as following, it occurs in the smart device itself. It doesn't send it to a cloud or something like that to be processed out of him. He himself process this data. So what does the smart device do? It fetches all the data from the API and it gets the frames from the camera. He looks for faces in the frame, and by recognizing the persons in the frame, it builds a report that he will send to the user's cell phone. So to do the biometry, he uses a Python module called face recognition. This module basically receives two faces and can tell if they are from the same person or not. And with this module, we can compare the face coming from the frame of the camera we can compare it with the photos that were submitted by the user and see if the user is in the photo or not. So now about the tests and results, when we were testing the software, it was quarantine. We were in quarantine in Brazil, so we had social distancing, and the tests were performed at home. These are the hardware specifications, and we had 3 test cases for this testing. And the first test, we try to evaluate whether the system is able to perform access control according to the authorized hours for an unidentified person. So what we do, we register Marcos for all day to be allowed all day, and when he passes through the camera, he generates an allowed report. Then we change it allowed time to be midnight to until 1 a.m. and it generated a not allowed report when passing through the camera. In the here we can see the message, the report that goes to Telegram. And the second test case, we evaluated whether the system is capable of handling access attempt by an unknown person. So we registered Marcos and we didn't register Adriana. When Marcos passes through the camera, it generates an allow report. When Adriana passes, it tells us that he doesn't know who the person is. So we can see. And the third case explored the system ability to issue an alert for identification of a certain registered person. So Marcos was registered but should not appear in the report. Adriana was registered and should generate a report. And when Adriana passes through the camera, it generates a report, and when Marcos passes, it don't generate a report. Here we can see. For the conclusions, we have built a system to command and control smart devices. It helped improve the security, and the test shows the system working as desired. And for future improvements, we intend to improve the face biometry to have better results with fewer photos. We intend to implement a mechanism in the camera coordinator that gives feedback of how the AI is doing, so it can regulate itself. And we intend to improve the smart device and the controller communication. This work was supported by the following, and thanks for your attention.